Good morning, everyone. So we will now start the cloud processes and precipitation session number 1 with a presentation given by Earl William on GNSS observation of deep convective timescales over the Amazon. And it's actually a presentation by David Adams, which I assume is not here, so you're giving the presentation, right? Okay.
Yeah, that's correct. Dave couldn't come, and he asked me to give the talk. And I just wanted to say that, to introduce David Adams. David Adams was a student of Milton Reno, many of you know, at the University of Arizona, where Milton used to be. And he also has been working in GNSS, stands for Global Navigational Satellite System, which is GPS, basically. So, by way of outline, this presentation essentially represents results from a recent study by Adams et al. With an extension to include preliminary results from the Belém GPM Chuva dense GPS meteorological network. We discussed first the motivation for the study, that is, creating a timescale metric for gauging deep convective processes in continental tropical convection. In particular, examining the timescale associated with the shallow to deep convective transition. We then outline the development of this metric, a water vapor convergence timescale. This timescale is examined for the Manaus region, where a 3.5-year deep convective climatology was developed, using data from the world's first long-term GPS meteorology station in the deep tropics. We'll finish by looking at some results from the diurnal cycle and sea breeze convection observed during the Chuva-Belém experiment. Models have had trouble reproducing the evolution of deep precipitating convection in the continental tropics. Oftentimes, convective parameterizations convect too early in the diurnal cycle or too frequently. This has effects on model dynamics and radiation schemes, as well as the precipitation distribution intensity. In many cases, the shallow to deep transition is skipped altogether. For large-scale models, what ultimately controls the model's ability to replicate the shallow to deep transition depends on the subgrid environment, which may have detrimental effects on cloud buoyancy. And just other contributions here. Karab-Udinov and Randall, 2006, in suggesting mechanisms for the shallow to deep convective transition, argued that when clouds are larger, entrainment was less important. Congested cold pools create a convergence zone leading to a deeper convection, and so on. And Wu et al. 2009 concluded that the critical lapse rate above the boundary layer was needed for a transition to deep convection. And so, of all these ideas, which argument is correct? It's difficult to say given lack of observations. One way to tackle this difficulty is through timescale analysis, an important result by Hohenegger and Stevens, 2013. Physical processes responsible for convective activity must have the proper timescale to jibe with observations. But these above and nearly all other studies are modeling studies and subject to all their uncertainties and representing deep convection. We need long-term, high spatial resolution, all-weather observations to carry out timescale analysis. And the GPS meteorology can help in this regard. Lost a little of that one. Okay. As pointed out by Hohenegger and Stevens, 2013, and Wu et al., it is critical to know the timescales of physical processes that are assumed to determine the shallow to deep convection. If the process is very important compared to the shallow to deep transition time, it can be assumed to be unimportant. On the other hand, if the shallow to deep transition is an intrinsic characteristic of the convection itself and the circulations it generates, then there should be an intrinsic timescale associated with this shallow to deep transition. Whether or not the shallow to deep timescale is intrinsic to convection or is reflective of the dominant external environmental factor forcing, we need observations in the first place to determine what the shallow to deep transition timescale is. This need helped motivate the present study. But what physical process, easily measurable and robust, can be used to set the shallow to deep transition timescale? We derive a water vapor convergence timescale, which can be easily measured with GPS. An equation which involves PWV, that's precipitable water vapor, or precipitable water vapor. The approximate equality here comes originally from, this is a loss term in the total water conservation equation. Then, again, focusing on the equation, the time rate of change of precipitable water vapor is a measure of water vapor convergence in the atmospheric column. But can the cloud growth term be considered small for deep tropical cumulus convection? We'll see from the results in the next slide. Composites of convective events over Manaus during the 3.5-year period using different criteria were made. What constitutes a convective event was based on a cloud top temperature criterion in addition to the appearance of surface precipitation or of a convective downdraft indicating precipitation. These convective events were subdivided and composited based on varying criteria to test the robustness of the water vapor convergence timescale. For example, diurnal versus nocturnal, intense convection degrees K per hour. In this case, the criterion is for high precipitable water vapor, moist cases, red solid lines, and low precipitable water vapor, drier cases, black dotted lines. Note that at around 4 hours prior to deep convection, which is here, deep convection is T equals 0, and T minus 4 is here, where the black lines are. The derivative of precipitable water vapor begins to rapidly increase, accelerating greatly 2 hours before deep convection. However, simultaneously, the derivative of cloud top temperature becomes more negative, i.e. cloud growth accelerates. If the cloud growth term were large, then the derivative of precipitable water vapor should decrease rapidly and even become negative. However, it does not. This supports our assumption that water vapor convergence dominates compared to the cloud growth term. The shallow to deep transition begins where vertical black lines are, and it terminates at T equals 0. Both are a bit longer than 4 hours. What criteria were used to determine this 4-hour time scale? We used where cloud top temperature first begins to drop continuously from above 280 K. Above 280 K represents low cumulus clouds or near surface temperature, 300 K. This represents the shallow to deep transition beginning time and is seen in the figure where the vertical black lines are. That is where the derivative first becomes continuously negative. This figure is as the previous one, however, based on a characteristic of convective intensity, in this case, events with very low cloud top temperature, less than 210 K, intense convection, and less intense convection, cloud top temperature greater than 230 K. From Adams et al., 2013, a wide variety of criteria were employed that represented environmental conditions in which deep convection develops and measures of the characteristics of the deep convection as shown in the present figures. Regardless of these criteria, the approximately 4-hour shallow to deep transition timescale appears. This argues for timescales as being intrinsic to convection. The difference in observed timescales for different environmental conditions or characteristics of deep convection is never different by more than 1 hour, always between 4 to 5 hours. At the longer 8-hour timescale, slow linear increase in water vapor is also observed prior to the onset of shallow to deep transition at 4 hours. However, this may be a diurnal signal. The 8-hour signal, surprisingly, also appears for nocturnal convective events. Nevertheless, it should be noted that the statistics for the nocturnal events are based on only 47 convective events, so it may be a statistical artifact, not representative of a real physical process. A dense GPS network was set up during Chuva Belém, as Luis Machado has reminded us. That was one of the early phases of Chuva, to examine convection in a sea breeze regime, very different situation from central Amazon, Manaus. 15 GPS stations were set up for about 6 weeks, late May to early July 2011, in and around Belém. This figure contains precipitable water vapor from the 15 stations as well as precipitation from a station in central Belém for a period of 5 days, up until June 19th. The diurnal cycle is quite apparent in the figure, with rainfall typically occurring around 5 to 6 p.m. local time at this station. A 12-hour ramp-up time on precipitable water vapor is notable. This figure represents the 6-week climatology of maximum precipitable water vapor observed from the dense GPS network during the Lane Chuva. The time progression of maximum precipitable water vapor from the coast towards inland is clear, a way of examining water vapor convergence due to the sea breeze. Current work in progress for Chuva Blaine. We are currently analyzing convective events from each of the Chuva GPS stations to increase the robustness of the statistics. Preliminary results looking at the shallow to deep transition timescale. Up to the present, several stations have been analyzed. Not surprisingly, the diurnal signal dominates. However, the next 4-hour shallow to deep transition is also observed, as with Manaus, lending credence to the intrinsic nature of the transition time. More stations need to be analyzed. Final results and first draft of paper by mid-June. There should still be a remnant dense GPS network at Manaus, about 10 stations, I think. This should provide a very unique possibility to examine the evolution of water vapor fields and convective evolution during Go Amazon 2014 and GPM Chuva at Manaus during the same period. The final slide is acknowledgements, and Dave particularly wanted me to thank Louis for his support in the early phases of the Chuva project. And this is the two of us over the Amazon River in Manaus. This is a very big river. And just another comment for those. One of the very interesting things about Manaus, for those who haven't been there, if you ever go to Manaus, don't miss the river gauge on the wall in Manaus Harbor. It's a very interesting and historical record of the variations in the depth of the Amazon River. Thank you very much. I'm not sure how well I can answer questions because it's not really my area of expertise, but I'll give it a try.
Thank you, Earl. Any questions or comments, maybe?
Or it's very interesting. You see the next presentation is the same line, but what is also interesting is the conversion from water vapor to precipitation, and it starts to happen before the time zero. If you move that, you see that it's a couple hours. Yeah, you can see at the time zero, the correlation, the variation start to decrease very fast. So it's really point to the time that water vapor is being condensated and liquid phase start.
Absolutely.